These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the annotation. Thank you. So the next thing I wanted to work on with you was resonance. That's an important topic in both semesters, and I think it probably would be important on the DAT as well. So let's start talking about that.
Okay.
So resonance is indicated using electron-pushing arrows, and reactions are indicated using electron-pushing arrows. So how do you know whether you're looking at resonance arrows or reaction arrows? I think I might have briefly mentioned this to you before, but the basic difference here, so here we have resonance, and here we might have a reaction. So resonance is not a reaction. These are two separate different things. So how can you see the difference between them? So resonance arrows involve only lone pairs and pi bonds.
Okay.
Resonance does not involve sigma bonds. On the other hand, every reaction involves at least one sigma bond. So we can put this in our notes. Tell me when you have that down.
Okay.
What do I mean by involves? Well, every reaction either breaks or forms at least one sigma bond. So resonance cannot break or form sigma bonds.
Okay.
So do these look like resonance arrows or reaction arrows?
Reaction. Well, yeah, reaction.
What was your thinking?
You're breaking a sigma bond on the bottom right. Carbon 2 and carbon 3 has a sigma bond that's breaking.
Yeah, you're right. So this would be a reaction because we're breaking this sigma bond. Okay, good. So this would be a reaction. But this reaction doesn't really make much sense because is this an acceptable leaving group?
No.
No. All right. So I didn't write down what I meant to write down. So, but yeah, this would have been a reaction. This would have been a reaction because we're breaking this sigma bond. Good. Let me write down what I meant to write down. All right. Now, would these be resonance arrows or reaction arrows?
Resonance.
Now it's resonance. Where are these electrons coming from? This negative charge represents electrons coming from a lone pair. So, and these is forming a pi bond and breaking a pi bond, and these head would form a lone pair. So this is resonance, not a reaction. Okay, good. Is this resonance or a reaction?
Reaction.
You can tell because this is forming a sigma bond. This is forming a sigma bond. Okay, now if you think about it, then anything with any reaction, anytime you have two molecules, it has to be a reaction, not resonance. Anytime you have two molecules, it has to be a reaction, not resonance. There's no way for two molecules to react without sigma bonds being involved. There's no way for two molecules to react without sigma bonds being involved. So resonance is always within just one molecule. Resonance is always within just one molecule. Is this resonance or a reaction?
It looks like a reaction. It looks like you're breaking the sigma bond, making that bromine a leaving group.
Good. And we're forming this sigma bond. Either would be good enough. Good. Now, this one I was trying to trick you because here there was only one molecule involved. So, but notice, even when there's only one molecule, it could be an intramolecular reaction.
Okay.
Is an intramolecular reaction the same as resonance?
No.
No, it's not. So this is an actual intramolecular reaction. It's not resonance. Because it involves sigma bonds.
Yeah.
Okay. So is this a reaction or resonance?
Resonance.
Is it an intramolecular reaction?
No.
No, because only pi bonds are involved. We're forming and breaking pi bonds everywhere. So this is resonance, not a reaction. How do you know that it's only pi bonds involved? Well, basically what you're doing, you might be doing here is, remember that we went over the rules for how to draw the product based on electron pushing arrows. Those rules still apply for resonance. So we know this is the type of arrow that's breaking a pi bond, and this is the type of arrow that's forming a pi bond. So this would be resonance. Okay, good. All right, so is this resonance or a reaction?
That looks like a reaction.
Why do you say that?
You're breaking a sigma bond.
All right, so that's good. So I was trying to trick you here. This is the most resonance-y looking reaction I could think of. So this looks like a resonance because this involves, here we're breaking a pi bond and forming a pi bond, and this is forming a pi bond, but still over here we're breaking a sigma bond. So this is a reaction. It's another intramolecular reaction.
Okay.
So your answer was correct. You didn't fall for the trap. This is a reaction because it does involve a sigma bond. Okay, so now we see how to tell whether something is resonance or a reaction. Very good. So next we should go over how to draw the other resonance structure based on the arrows. Now the good news is that we probably don't need to spend too much time on that because the rules for interpreting resonance arrows are identical to the rules for interpreting reaction arrows. And we already spent a lot of time on how to interpret reaction arrows. But let's practice that a little. So let's try that on this example. Try drawing the product here. Or actually, it's not a product because it's not a reaction, but try drawing the other resonance structure based on these arrows. So on your screen, try drawing the other resonance structure based on these arrows.
Okay. Seems like for resonance, don't you do a double-sided?
Terrific. That's good that you thought about that. It's good that you're thinking about the correct symbols. That doesn't seem very exciting, but that's actually quite important. So that's right. Resonance is not a reaction, and we want to indicate that by using a different type of arrow. So that's right. That's the correct arrow to use.
Okay. Thanks. Okay.
Okay, excellent. Very good. So that came out exactly right. Excellent. So we've just gone over the rules for how to interpret electron pushing arrows, and the rules are the same for reaction and for resonance. So you use the same rules here. How many charges did you change?
2 charges.
Just like you would have if this was a reaction. So you did that correctly. Very good. I'll go back to my screen, and that was a good use of the double-headed arrow. Good. So here was another resonance structure. Try drawing the other resonance structure based on these arrows.
Okay.
Okay, good, excellent. Go back to my screen. Why did you not change 2 charges here?
It was cyclic.
A cycle of arrows. We talked about that for reactions as well. When you have a cycle of arrows, you don't change any charges. So you did that correctly. Okay, now let's talk about the interpretation then of resonance. What does resonance mean? How is this different from a reaction? Well, here's the key thing. Maybe let's compare this with a reaction. So maybe we can compare it, say, with this reaction here. The key difference is that in a reaction, things are changing. Here we have starting materials, and here we have a product. We're changing from this picture to this picture. But resonance is not like that. Resonance is more subtle. Resonance is not a change. The molecule is not changing from this picture to this picture. In fact, I would say that even though this is the correct symbol, it's probably not it's not really a good symbol that the chemist chose. I think this is a poorly chosen symbol because it makes it seem like we're changing back and forth between these 2 pictures. But we're not actually changing back and forth between these 2 pictures. Resonance is used when it's impossible to draw a true picture. So remember that all of our pictures are just models of the real molecule. All of our pictures are just models of the real molecule. It's kind of amazing that any picture we draw is really a good model for the molecule. When there's resonance, no one picture by itself is a good model for the molecule. So we need to use resonance to get a better mental picture of the molecule. So the molecule is not changing back and forth between these 2 pictures. The true molecule is a blend of these 2 pictures. The true molecule is a blend. So the molecule doesn't change from here to here. The molecule is just one thing, which is a blend of these 2 pictures. So to give you an example, for example, what is the real formal charge on this oxygen? What is the real formal charge on this oxygen? Well, in this picture, the oxygen has a negative formal charge. And what's the formal charge on the oxygen in this picture?
No charge.
So what's the true charge on the oxygen? In the real molecule, it's somewhere between -1 and neutral. So that's what I mean by a blend. The true oxygen has a partial negative charge, I guess you might say. The true oxygen has a partial negative charge somewhere between neutral and negative. And then, for example, what's the formal charge on carbon-3? Well, in this picture, carbon-3 has a negative formal charge, and in this picture, it's neutral. So in the true picture, carbon-3 it has a partial negative charge, again, somewhere between neutral and negative. So the true picture is a kind of a blend of these 2 pictures. All right. You still there?
Yeah.
Okay, good. We could say something similar here. What type of bond is there between 1 and 6? Is the bond between 1 and 6 a single bond or a double bond? So in this picture, is it a single or a double bond?
Single.
How about in this picture?
Double.
So And we haven't talked about this, but do you know what's stronger, a single or a double bond?
A double bond.
Double bonds are stronger. That might be intuitive because they've got more bonding. So how strong is this bond? Well, because it's between a single and a double bond, the true bond can't be drawn. The true bond is somewhere intermediate in strength between a single and a double bond. The true bond is somewhere intermediate in strength between a single and a double bond. Maybe this isn't the best example, though, because it also involves aromaticity. Maybe I shouldn't have used that example. So actually, let's put that aside, because this has another issue. It also has aromaticity. So let's actually maybe just go back up to this example right here. How strong is the bond here between carbon 2 and the oxygen? Well, in this picture, this is a single bond, and in this picture, it's a double bond. So in the true molecule, its strength is somewhere between a single and a double bond. It's not exactly like a single or a double bond. It's kind of a mixture of them. And the same for the bond between 2 and 3. In this picture, there's a double bond between 2 and 3. In this picture, there's a single bond. So in the true picture, it's a kind of a blend of a single and a double bond, intermediate between a single and a double bond, which is difficult to draw. Okay, so hopefully we're seeing then that in order to picture the true molecule, you kind of have to picture a blend of these two. So an example that I've seen that I think is a good example is, let's say that you were trying to describe a nectarine to someone who's never seen one before. How would you describe a nectarine to someone who's never seen one before? And let's suppose that you can't just draw a picture. I'm not a good enough drawer to draw a nectarine. So how could you describe a nectarine? Well, you might say that a nectarine is a kind of a blend of a plum and a peach, if you see what I'm saying.
Okay. Yeah.
It's kind of a blend of them. On the one hand, it has a skin that's smooth like a plum, but on the other hand, it tastes more like a peach. So it's a kind of a blend of a plum or a peach. This is not a perfect analogy, but it kind of gives you the idea. So you might almost say a nectarine is like a resonance structure of the plum and the peach could be considered different resonance structures of a nectarine. All right, not a perfect analogy, but that gives you the idea. The key thing is, here's the point. Are we trying to say that a nectarine changes back and forth between looking like a plum and looking like a peach?
No.
No. So that's the key point of this analogy. Resonance does not mean you're changing back and forth. So this is not, that's why I thought this is actually not a great symbol. This is not a well-chosen symbol because it makes it seem like we're changing back and forth. You know what I think would be a better symbol? An equal sign. So if I was the king of chemistry, maybe we would use an equal sign to show resonance. Because what we're trying to say is these are just two different pictures of the same exact molecule.
Okay.
These are just, it's almost like this. These are two different pictures of the same number. Well, these are two different pictures of the same molecule. So it might be better to think of it as this an equal sign. These are just two different pictures of the same molecule. So it's maybe unfortunate that historically we're using this double-headed arrow because it makes it seem like we're changing back and forth when we're not.
Yeah.
Okay. So that gives us a basic sense then. So notice that's very different from a reaction. This is an excellent symbol for a reaction because we really are changing from the starting materials to the product. So a reaction really does involve a change. And this arrow is very appropriate for that. So notice that for reactions, we use this type of arrow. And for resonance, we use the double-headed arrow. Even though I've said this isn't a very good symbol, we have to use it because that's what everyone else is using. So we use a double-headed arrow for resonance and a single-headed for reaction. But we have to keep in mind the double-headed arrow is a little misleading because we're not changing back and forth between the two pictures. Instead, the true molecule is a blend of the two pictures. Now, why do we care about resonance? Why do we care about resonance? Well, what's the most important factor in organic chemistry?
The charges.
So why do we care about resonance? Because it reveals hidden charges. That's one of the reasons anyway. One reason we care about resonance is because it reveals hidden charges. For example, suppose you only looked at this picture. Then you would think that the only charge was on the oxygen. But the resonance reveals there's a hidden charge on carbon 3. So that's one of the most important reasons to care about resonance. It reveals hidden charges. We always keep coming back to the charges. Why do the charges matter? Well, let's say you looked at this picture. Based on this charge, what role would you expect this oxygen to play in a reaction?
Nucleophile.
Maybe a nucleophile because of the negative charge. And what other role might it play besides nucleophile?
Base.
Because negative charges make things nucleophiles and bases. So
Yeah.
who would we expect to be the nucleophilic atom? Who would we expect to be the nucleophilic atom? Well, if all you saw was this picture, you would expect the oxygen to be the nucleophilic atom. But the resonance reveals who's the other nucleophilic atom.
The carbon.
Let's use the numbers to be specific. Which carbon?
Carbon number 3.
That's right. So that's why that's one of the most important reasons why resonance matters. Resonance introduces hidden charges that give you different possibilities for who can be the reactive atom. If you had never learned about resonance, you would assume that the oxygen was going to be the reactive atom here. Maybe I shouldn't have those arrows in the same picture, but if you were looking at this molecule, you would expect the oxygen to be the reactive atom. But the resonance reveals that maybe it's carbon 3 that will be reactive rather than the oxygen. So that's one of the most important reasons to go over resonance, because it helps us now to predict more reactions, because we can see atoms that will react that we might not have predicted because they have these types of hidden charges. So the next thing for us to do is, I think you pretty much already know how to draw the product based on the resonance arrows. So the next thing for us to do is to start learning how to come up with the resonance arrows on our own. So I guess that would be a good thing for our next session, to go over how you can come up with the resonance arrows. Because after all, in this example, I drew the resonance arrows for you. So now we need to go over how you could have come up with these resonance arrows on your own. Or in this example, I drew the resonance arrows for you. So next we have to go over how you could come up with those arrows on your own.
I just have one question. That second example that you gave with the bromine there, actually, yeah, the oxygen with the negative charge, where your mouse is now, would that happen? It seems like that would rather attack that carbon right next to the bromine, at least from
this one here.
Yeah.
Because of the delta positive.
Yeah.
Yep. That's a good point. So this kind of breaks some of the rules that we talked about before. So this is not something you could have predicted earlier. This is a real reaction. This is a real reaction that actually happens. It doesn't quite fit all the rules that we talked about before. That's good that you were thinking about that. That's excellent you were thinking about that. How could we see how this does make sense? Notice that we're still able to use the good leaving group here. We're still able to use the good leaving group. I don't know. Actually, maybe it's hard to explain. So I would say this is a reaction that's sometimes studied that you would just kind of have to memorize. It doesn't fit our previous rules. So we do have a good leaving group here. We do have a good nucleophile. You're right that we would have predicted the oxygen would just attack this carbon directly. But in this reaction, something different is going to happen. So what you're predicting is what's called an SN2. And what I drew is what's called an SN2 prime. Actually, some classes cover that and some classes don't. Okay, so anyway, you're right. Based on the rules we talked about before, you would have expected this carbon to be the electrophile. But this just happens to be another reaction, another type of pattern that we hadn't talked about before.
Okay, great.
This reaction, actually, this is a little bit of a rare reaction. Most courses don't cover this. Some introductory courses cover it, some don't. The only reason I wrote this, I was trying to come up with reactions that looked as much like resonance as possible to fool you.
Oh, okay,
so that's why, if I had drawn it like this, I don't think there would be any way that no one would be fooled into thinking this was resonance. So I came up with a little bit of a weird looking reaction because I was trying to make it hard on you, because this was to test whether it was resonance or a reaction. So that's why I came up with this kind of somewhat weird, a little bit unusual reaction. All right. Okay. But yeah, it's good that you're trying to apply the rules that we talked about here. So yeah, it is a little bit of an exception to the rules we talked about before. Okay. The important thing is that, though, it's good that you're trying to apply those thought processes. You can see though it is a little frustrating. We have to accept that in organic chemistry there's rules and there's also many exceptions. So we do have to accept that as you go through your course, you will see reactions that don't fit all the rules that I've taught you before. You just have to accept that and learn those as exceptions. That's why organic chemistry is complicated. It's very valuable to learn the rules. The rules apply in many cases, but there's also many exceptions, and we just have to be flexible and adapt to that. So this would not fit the exact patterns we talked about. Okay, but it's good that you were trying to think about that.
A lot of this reminds me, I don't know if you've done a lot with like music theory, but a funny thing about music theory is that they often go over so many rules, but you learn the rules and then you break them because there are always exceptions.
That's an interesting analogy. Yes. So I haven't studied it at all, but it sounds kind of like maybe like the rules for writing. You know, like if you take a writing course, they teach you all these rules, but then, you know, when you're a good writer, you also know when to break the rules. So so that's right. So yeah, the one difference is I think like in music theory, you're learning kind of how to make good music or good sounding music, or in the writing course, you might be learning how to make write something that is good. Whereas here, we're not trying to come up with a good reaction, so to speak. We're trying to predict what does nature actually do.
Sure,
but
yeah.
So instead of learning so in your music theory class, you kind of learn when you choose to break the rules to make something sound good. Whereas here, you kind of have to learn when nature is breaking the rules. But yeah, actually, I like that analogy. That is interesting. So that's why those are challenging. Yeah. So this is a challenging subject. And other subjects like music theory could be challenging as well because there's many rules, and then there's still many exceptions. But even though there's many exceptions, that doesn't mean that you don't need to know the rules. So that is a good comparison. That's good.
Yeah.
I'll have to think about that.